Thanks, the organizers, for inviting me, and thanks everyone for coming. I'll talk about a series of 3 papers which performed the first 2-loop scattering amplitude calculation for spinning binary dynamics. I'll also talk about ongoing work which revealed that these amplitudes have a surprisingly rich set of symmetries, which we are able to connect with integrability of classical systems, but we have yet to understand fully. The work is in collaboration with my PhD student, Dogan Nakpina, and other collaborators, including Graham Brown in the audience, Fernando Febres Cordero, Ricardo in the audience, Manfred Krauss, Wanda Lin, Mikhail Ruf, and Alexander Smirnov. I'll give a bit of a background. I'll talk about our 2-loop amplitude calculation. I'll be relatively quick on this part. I'll talk about our application of the recently proposed covariant Dirac bracket formalism to extract classical observables out of these amplitudes. And I'll talk about unexpected symmetries, which we accidentally discovered out of our amplitude calculation. We know that since 2015, gravitational wave physics has progressed at a rapid pace. This plot is already several years old. It showed 90 events from black hole or neutron star mergers. And at the end of the 04 run, expected to end October this year, more than 200 events will be expected. There are many future detectors planned. They promise to push the strain sensitivity by orders of magnitude. And they will enable much more precise measurements of the waveforms, and they will allow us to see much further back in time in the universe in the redshift scale. To meet the challenge of making waveform predictions, we need improvements across the board, for example, in numerical relativity, but also in the in-spiral perturbative regime, which can be too long to be feasibly modeled by numerical relativity simulations. So the perturbative studies will be the focus of our talk. Quantum field theory has emerged as a powerful tool. By now, we know that for post-Newtonian expansions, there is the powerful tool of non-relativistic general relativity invented by Goldberger and Rothstein nearly 20 years ago. For the post-Minkowskian expansion, which has traditionally been quite difficult for direct classical calculations, we made a lot of progress. A lot of people, including many people in this audience, in the last 7 or 8 years, using on-shell scattering amplitude methods. We are often able to produce results beyond the best from the direct calculation in classical GR, although, of course, also vice versa. The topic of this talk is the third post-Minkowskian binary dynamics to the 4th order in Spain from 2-loop amplitudes and the symmetries in the amplitude. So what we are calculating in the scattering setup is 2 Kerr black holes incoming with impact parameter B with some velocity generally parameterized by some relativistic gamma factor, and with arbitrary spin vectors, which may not be aligned with orbital planes. This scattering observables are gauge invariant because they are defined at t equals plus or minus infinity, but they are relevant for real gravitational wave detectors, not just because there might be future detection of rare scattering events, but also because for the actual bound waveforms that are routinely observed, there are a variety of methods to go from scattering to the bound problem, for example, via analytic continuation, or alternatively, via matching to a 2-body Hamiltonian that works equally for the bound and unbound cases. There are many scattering amplitude approaches to spinning black holes, and I apologize in advance that many of you won't be acknowledged. Sorry. Okay, thanks. So one influential formalism is the massive spinor helicity formalism by Akane, Hammond, Huang, and Huang. What's good about it is that you can write down amplitudes to all order in spin via spin exponentiation. For high loop calculations, this is actually challenging because the tensor rank grows linearly with spin without bound. It's not a problem for tree level and one loop calculations because there's this wonderful contour integration formula by Darren Ford and later rediscovered by Alfredo Guevara as the holomorphic classical limits. There's some contour integration formula which allows you to extract coefficients of master integrals very efficiently. But at two loops, we fall back to conventional IBP reduction. And the most straightforward setting is reverting to the use of finite spin massive particles, which have a long history. In this setup, if you go to a spin J massive particle, you can access 2J orders in the perturbative spin expansion. For example, if you go to spin 2, which is the largest spin that is without any subtlety of higher spin complications, you can access the quartic order in spin. Although this is the older method, there's something new that we have to find out about it. It's that in this method, there's a lack of a mechanism for taking the large classical spin limit. So in the most naive application of this method, you are plugged by an ambiguity over the spin Casimir terms. The spin Casimir terms basically commute with everything, and naively they are confused with the spinless terms in your calculation. And we devised a method to solve this problem, as we will cover in the next slide. And there are also approaches outside amplitudes, just for completeness. I think I need to refocus the. Okay. So now at tree level and one loop, very high spin orders have been reached, sometimes to all orders in spin, but only a handful of results exist at two loops. As the earliest paper published was from Worldline quantum field theory by Gustav Jacobsen and Gustav Mogel. A few months later, we published the first calculation based on scattering amplitudes, also for the conservative dynamics, also to the spin squared order. And very recently, a few months ago, we were able to push this to the unprecedented quartic order, which has been established for a few years at the one loop level, but this is but now we can do it at two loops. And this physically corresponds to the seventh post-Minkowskian order if you identify the maximum spin of an extremal black hole with the Schwarzschild radius or the ring radius. Okay, and just to flash briefly, we identify Kerr black holes at least to the first four orders in spin as minimally coupled massive spinning particles, minimally coupled to gravity. We have a Klein-Gordon action for spin 0, Proca action for spin 1, and Fierce-Pauli action for spin 2 massive particle. In our as an initial calculation, we have one spinning black hole and one spinless black hole. So we calculated the scattering amplitude with the spin 0 particle and the spin 2 particle. We used an automated engine called Caravel which has been applied in many cutting-edge collider calculations, especially 2 loop 5-point calculations. But it can also be applied to gravity. It's based on Baron-Skiller recursion for the cuts, but we also have checked the cuts against the double copy plus dimensional reduction to reduce gravitons to massive spinning particles. After the integrand is obtained, we perform soft expansion and IBP reduction. The IBP reduction is not as hard as some of the calculations like the for-loop spinless calculation, but still pretty demanding with complexity over 20. And the IBP problem was solved using a private version of FIRE, which I've been developing with Alexander Smirnov. But that's the end I'll talk, say about the amplitude themselves. Now I'll move on to how we extract physics out of the amplitudes. Now, briefly, I need to mention that we need to do some Lorentz boost to convert the polarization structure of the amplitudes to an interpretation in terms of classical spin. One way to think about it is that if you think about the K-Mach formalism, you have some wave packet centered around some momenta, but you also need some polarization state. We take a single polarization state for simplicity. There is some polarization vector epsilon I, and you can extract the Pauli-Lubansky vector out of this polarization vector, and that's what will be identified with the classical spin. But this classical spin involves the same polarization vector appearing twice, one time with a complex conjugate. But what comes out of amplitudes is that the outgoing state will have a slightly shifted momentum Q because of the graviton exchange compared with the incoming state. And this is handled by doing a Lorentz boost to rewrite the amplitude in terms of the polarization vectors with respect to the same incoming momentum. Okay, so that's as much time as I have to devote to this. Now the amplitudes have already been turned into an object, which are expressed in terms of the classical spin. Now I have to solve a little problem with low spin, finite spin calculations. The problem is that the classical spin is a large spin because in the classical limit, it's the correspondence limit of quantum mechanics. All charges become large. The spin will, as a unit of h bar, will also need to become large. So as h bar goes to 0, this s needs to scale as 1 over h bar. So this is actually an object that scales as h bar to the 0 classical power. But if you use a low spin classical particle, this becomes, this s squared is a small integer, and this becomes mixed with quantum suppressed spinless terms. So the solution is actually pretty simple. We just keep further orders in the soft expansion to keep the quantum part of the amplitude to enough orders. And we extract a gradient with respect to s squared by calculating the same amplitude with several different spin representations. The gradient is the physical information proportional to the classical Casimir terms. And the intercept is truly quantum, which we discard. Okay, and this can be pushed to the also higher orders in spin with some subtleties, which we won't go into here. Now, so this amplitude is expressed in terms of classical spin, and with this Casimir ambiguity also resolved. Now we want to extract classical observables. There are established methods like non-relativistic effective field theory or the K-Mach Kosawa-Maybe-Okano formalism, but they are rather, let me say, a little bit tedious to apply at higher loop orders. And we want to look for easier methods. One method mentioned by Andres is using the Eichner exponent as a generating function, which encodes all the observables, including impulse and spin kick, etc. And so far, it has only been worked out to one loop order. We propose a simple, we conjecturally propose a pipeline, which we believe to be both simple and work to all loop order for conservative dynamics with spin, where we extract the radio action from the finite part of the amplitude, and then we turn the radio action into observables using Dirac brackets, which Ricardo will cover in more details later in the conference. So this amplitude action correspondence was what collaborators and I first proposed in the 21 paper of the fourth post-Minkowskian calculation of spinless dynamics. It identifies the radio action with a suitably defined finite part of the amplitude. So at 3 loops or higher, it gets a little bit sophisticated. You need to extract a finite part out of certain boundary conditions for differential equations. But at 1 loop and 2 loop, the prescription is exceedingly simple, as we showed in the paper in collaboration with Andres and Enrico in the audience, also Zvi and Juan Pablo Gatka. Up to 2 loops, we just need to keep the finite master integrals after the soft expansion and IBP reduction, and throw away the divergent integrals. And that's just it. What you are left with is the radio action up to a Fourier transform. This is actually equivalent, we soon realize, to the exponential representation of the S matrix proposed by Damga and collaborators, where they noted that since the S matrix is unitary, formally you can write it as an exponential of I times the Hermitian operator. And this Hermitian operator is identified with the radio action. Now, to extract the observable, you in the K-Mock formalism, you extract the change of the expectation value of some observable in the out state and the in state. Writing S as exponential of In, so this is the change, delta O. And if you perturbatively expand this, this becomes an infinite sum over iterated brackets. If you want to keep to the nth order in the gravitational constant, you truncate the infinite sum at the nth order. So now what we want to do is that, since we recognize that this exponent, so the scattering amplitude itself has divergences, but this exponent is actually has a finite classical limit. So what we want to do is that starting from this the classical part of this n, and we also take the classical limit of these quantum brackets to do a manifestly classical calculation to extract the observable. So what's the classical limits of quantum commutators? The first thing that comes into your mind would be Poisson brackets. That is almost right, but not quite right. And that's responsible for a lot of confusions in the literature. And as a pair of 2 groups showed last year, the Dirac bracket, which is a kind of modification of Poisson brackets, as applied by Hanson and Reggie to the relativistic spherical top in the 1970s, actually give the correct classical limit for these brackets. And we believe that it works to all orders. So Ricardo will cover this in more details later in the conference. But we start with simple Poisson brackets, and then we impose constraints. For example, the impact parameter is orthogonal to the velocities, and the velocities are normalized, and there are also things like spin supplementary conditions. Now you just feed these things into Dirac's formulas proposed in 1950, which turned the Poisson brackets into Dirac brackets, and that solves the problem. And we get the classical observables out. We've checked our results against a lot of literature. For example, the very recent post-Newtonian calculation last year, if we expand our results in small velocity, the first few terms in velocity expansion agree with the post-Newtonian results. And to check the validity of brackets, we also checked against K-Mock at lower spin orders, as well as Worldline quantum field theory. Okay, thanks. Also, we observed the cancellation of high energy divergences in observables through the quartic order in spin. So this was kind of a controversy 6 years ago concerning the first two-loop calculation of spinless dynamics. Eventually, people agreed that high energy divergences cancel between the conservative contribution and the radiation reaction contribution. And this is now seen to the quartic order in spin. So in the last few minutes, I'll mention that the amplitudes have some surprising symmetries. For example, this S1.q squared, so S1 is the spin of the particle 1, and Q is the exchange momentum, has an exact coefficient, which is the exact negative of the coefficient of Q squared S1 squared. This was nicely identified as a symmetry principle, spin shift symmetry, which Andreas mentioned in his talk. We confirmed that this symmetry actually exists beyond one loop. We see the symmetry in our two-loop calculations, but only in the probe limit when we ignore the first cell force corrections, which were not accessible in one loop calculation. So this clarifies the nature of the symmetry a lot. It ties the symmetry with the probe limit, specifically a probe Kerr black holes, because for neutron stars, the non-minimal coupling also breaks this symmetry. So could it be integrability? Because people have made similar observations that for a probe black hole, but not neutron star, the classical motion is integrable. So in the Schwarzschild case, it's obvious because they are killing vectors, giving you energy azimuthal and total angular momentum conservation. For Kerr, there's only azimuthal angular momentum conservation. The latitudinal part of the angular momentum conservation is lost. But actually, there's a Killing tensor, which is a more subtle form of symmetry, which gives you a conserved quantity, which makes the motion integrable again. And this has been shown in the 80s to extend to the linear order in probe spin and the quadratic order in the probe spin by Justin Vines and collaborators 2 years ago. But we see that these mysterious symmetries show up even to quartic order in spin. So let's ask the question, is it possible that the integrability of Kerr orbits actually hold up to much higher spin orders than what people previously imagined? Now, this is where the Dirac bracket formalism becomes very useful again, because the change of the observable is given by iterated Dirac brackets of the radial action with the observable. If the observable, if the radial action you calculate commutes with the observable, then it won't change during scattering. So we can test all the three observables as mutual angular momentum, Carter's spinning generalization of Carter's constant, and there's also Rudiger's first invariant, which only exists in the presence of spin. We find that to the quartic order in probe spin, these three conserved quantities always commute with the radial action. So we were able to extend the previous integrability knowledge from the quadratic order to the quartic order in probe spin. Although I have to say that this is conjectural, although we have observed this from tree level 1 loop and 2 loop, we have no guarantee that it's not going to break at 3 loops. Thanks. Although if things hold already across 3 loop orders, I think we are fairly confident. We also showed that if only one of the black holes has a spin, and at the second post-Minkowskian order, the motion is integrable even without the probe limit. And this again goes beyond integrability observations in the post-Newtonian literature. And now I just briefly mentioned that. The effort to investigate the spin shift symmetry led us to these rich symmetries related to integrability. But at the end of the day, we realized that there are extra symmetries They are not a spin shift symmetry. And if we combine them with spin shift symmetry, they become very powerful. And the integrability symmetries are natural in position space, and the spin shift symmetry are natural in momentum space. So maybe there's some analog to an n equals 4 super Yang-Mills theory, where there are ordinary and dual conformal symmetries naturally formulated in position and momentum space, respectively. So in conclusion, we did the first calculation of the two-loop conservative dynamics to the quartic order in Spain. We applied Dirac brackets to effortlessly extract observables. We observe a rich set of hidden symmetries accidentally. We don't fully understand them, and we'd like to understand them better in future. And we believe that we can start a new on-shell approach to hidden symmetries in classical systems. Thank you very much.